This video continues our conversation about the structure of the periodic table. On the screen here you see the first 3 learning targets for this unit. I can understand the basic organization of the periodic table, I can locate the key groups on the periodic table and identify their properties, and I can distinguish between metals, nonmetals, and metalloids. This video will mostly focus on the second one here, but obviously it's leading into a little bit of the basic organization also. And metals, nonmetals, and metalloids is hopefully something that you can do by this point. Okay? So, what are the key groups on the periodic table? Well, the first key group that you should know about is the group called the alkali metals. They are group 1, meaning if you look at your periodic table, they are the column all the way to the left. Okay, so the columns are referred to as groups or families. So the alkali metals are lithium, sodium, potassium, rubidium, cesium, and francium. Now, it doesn't include hydrogen. If you look at this group, hydrogen is in the column, but hydrogen is not really considered part of this family. Number 1 reason, hydrogen isn't a metal. Now, it does a lot of the same reactivity that these alkali metals do, but it's not considered part of the family. It is not a metal. So, what similar properties does this family have? They're all very highly reactive in water. Okay, if you put them in water, they will start fizzing and sputtering and a lot of times igniting because they're emitting hydrogen gas as they react. You potentially have seen a video of lithium or sodium reacting before. I will show you a video in class of all of these in series as they react. Okay. Another one that's similar is that they burn in the air, right, which I just said they can ignite as they work with oxygen, or sorry, as they mess with the water. If you actually see a physical sample of this material, and here are 3 different pictures of the physical samples, they're very soft metals. Okay, very easy to cut, very easy to manipulate and use for things. Very shiny. Okay, they look like metals. We use obviously lithium for like lithium ion batteries. Okay, very easy to mold and use. The thing that's in common about them in terms of their actual chemical structure is the fact that they only have 1 electron in their outermost energy level. So if you take a look at this board behind me, it has all of their electron configurations listed out. Okay, some are in noble gas, some are complete. But you'll notice here that their last electron for each of these is just 1 electron in the s orbital. So their outermost energy level, or their valence energy level, only contains 1 electron in the s. So their reactivity is actually based on this 1 electron in the s, and that's why they all do similar things. Now, part of this unit will be for us to understand trends in the periodic table, meaning, yes, these all react, but how is their reactivity? And what we find is going down the table, so going from lithium down to francium, their reactivity increases. Meaning while sodium burns in water and may light on fire, cesium, when it burns on fire, actually can ignite and explode material. Okay? So their reactivity increases as you go down the group. Okay? And the thing that's similar about them is that S1 for every single one of them. And I'll show you this video when we get into class. The next group is the next column over. Okay, so moving from the left, that second column, and they're called the alkaline earth metals. Most common mistake for this test is just interchanging alkali and alkaline earth metals. So make sure you keep those 2 distinguished for yourself. So the alkaline earth metals are this is column 2, right? Beryllium, magnesium, calcium, strontium, barium, and radium. How are they all similar? Well, basically they're going up 1 step from the alkali to the alkaline. Rather than being very soft metals, these are much harder, stronger, and more dense metals. Okay, kind of increasing the density simply because they have that 1 more proton over the alkali metals. That can lead to their more dense compactness. And they're harder and stronger, partly because of the fact, then we look at their electron configuration, they're just a little bit more stable. Okay? Because they're a little more stable, they have a higher melting point. They tend to be less reactive than the alkali metals, but they do similar reactions. They can still burn in water. They can still react with water. They still can ignite in the air. We will do a lab where we ignite magnesium in the air. So they do the same chemical reactions as the alkali metals do, but they do it just less violently, less quickly, less well, in our opinions. They don't do it quite as well. So if you take a look at the electron configurations for the alkaline earth metals, you'll notice here that the difference between the alkali metals and the alkaline earth metals is that the alkaline earth metals have S2 as their outermost energies. Okay, their valence electrons, those electrons that exist beyond the noble gas, contain 2 s electrons rather than just 1 s electron. Now, they do not have a complete outer energy level then, right? This is just a complete sub-level. The S sub-level is full, giving it the teeniest bit of stability over the alkali metals. Meaning they will still be reactive, as I mentioned, they'll still do the same things, but their tendency is to do them not as strongly. They just don't react as strongly as the alkali metals would because their sublevel S is full. Something I'll mention when we get to halogens, but I'll mention it here also, is that one of the goals of all of our elements on this periodic table is to get a full energy level, meaning a full S and a full P. These guys have a full S but not a full P, which is why they will still be reactive even though they have a full sublevel. Okay, so they're still going to do the reaction, just not as vigorously. Their properties are still shiny, metallic, dense, and that's kind of the properties this group shares. The third group you're responsible for knowing something about are the halogens. They're right here in column 17 or group 17. So if you go all the way over to on your periodic table to the column right before the column that contains the noble gases, those are all called halogens. Halogens mean salt formers. I'll talk about that in 1 second. But the halogens as listed here are fluorine, chlorine, bromine, iodine, and acetine. Okay. We're now in the part of the periodic table which are called the nonmetals. So these are nonmetals, all of them. They are the most reactive nonmetal group. Okay. Part of the reason they are our most reactive nonmetal group is because of the fact they have 7 electrons in their outermost energy level. So let's take a look at the electron configuration for these. This is fluorine, chlorine, bromine, iodine, acetine. This is one of the man-made ones that we don't really have a name for yet. But if you look at all of these, we have P5, 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 P5. Okay, that's their last shell is P5. When we say 7 electrons at their outermost, what we mean is they have 2 in S and 5 in P. That adds up to be 7. When you're down here, right, in these 3, you can see that they have some in D's and some in F's. We don't generally count the D's and the F's when we talk about their valence electrons. A lot of reasons, mostly because when we make ions, remember we talked about making ions, when you make ions you go from P then S, then D then F. So P and S are really the 2 sublevels that we're taking and adding electrons to, P and S. So because of that, when we're looking at how it's going to react, we're really going to look at P and S. D and F will affect its reactivity, but as I've said before, the way it affects it are kind of outside the realm of what we will be studying. We will be studying how elements react based on their S and their P. So for halogens, their S and their P always add up to be 7, meaning they are 1 electron away from having a complete P orbital and being like a noble gas. One of the goals, as I'm going to tell you when we talk about ions, of every element on the periodic table is to become as stable as a noble gas. And how they become as stable as a noble gas is by having their S and their P, outermost energy level, full. So halogens are just one electron away from having their S and their P full, meaning they are very highly reactive because it is not as difficult to take one electron away from something as it is to take like 2 or 3 or 4, for example. So if they can rip one away, they got it. Okay, so they are very reactive. They are salt formers because salts are essentially compounds that contain a metal and a nonmetal. And since these are our most reactive nonmetal group, they are the ones that predominantly are making salts. Right? They are the ones that are bonding with a metal to make a salt. I'll show you how to make salts when we deal with compounds and naming, but for now just understand that a salt is a metal with a nonmetal, and this group, since it's so highly reactive, is going to be the ones bonding with your metal to make salts. The last group you're responsible for knowing anything about are the noble gases. They are the last column on your periodic table, group number 18. You already know where these are. We needed to use them for the noble gas electron configuration, but here they're listed again: helium, neon, argon, krypton, xenon, and radon. Okay. These ones, because of kind of general discoveries of them, were thought to be completely unreactive for a very long time. Now, in later years, we've been able to get xenon and radon to do some reactions by utilizing their larger orbitals, not just their P and their S, but using their D's and their F's to do things. They can potentially take on bonds. But the rest of them really are considered non-reactive. General practice is they don't bond with other things. And the reason they don't bond with other things is because their outermost energy levels are full. Their S and their P have no more room for electrons. And because they have no more room for electrons, and the additional electrons would have to jump up an energy level, which is usually a substantial jump in energy, they don't want to. Okay, they just don't want to. So here are their electron configurations on the board. You notice all of them end in P6 except for helium, which has the 1s2. Now that's still a complete energy level because one only has S, doesn't have P, so helium is still a noble gas even though it's kind of different than the rest of them. Okay. Number one, the thing that's unique and cool about noble gases is that they're a gas at room temperature. Okay. A lot of our nonmetals are potentially gases, but noble gases are always gases. So that's one thing about these particular elements. Because of their stability and their being found as gas, they have lots of practical uses. Number one, potentially you've heard of neon lights, right? The neon gas is used in lights. They put the gas in, they send electricity through it, and the neon lights up. They can also do this with argon. A lot of light bulbs will actually be placed in an environment of argon within the glass bulb, and that's partly helps the light transmit and keeps it from wasting energy. We know we use helium and helium balloons. We could use hydrogen. It's also a very light element that's a gas, but the main difference between hydrogen and helium is the fact that hydrogen, because it has one electron in its s orbital, is flammable and will explode, where helium will not. It is not a gas that is going to ignite, so it's much safer to use. Fill a balloon with helium at your child's birthday party, and you're not so nervous as filling a balloon with hydrogen. Even though they would do the same thing, they're both light, they would both float. But helium is actually a much safer gas for our use. In the bottom picture with the welding, when you're creating that much energy and heating things up, you have to be wary of the oxygen that's around it. Lots of things react with oxygen. So a lot of times you're actually placing whatever you're welding inside an environment with like argon gas or even krypton gas to keep it away from the other gases in the air. That's it for now for your 4 main groups. You should be able to recite from memory some of the basic chemical properties and physical properties for each of the 4 families or groups. Okay? Have a nice night.